In this segment, we're going to look at the connection between electric field and electric potential, and we'll start with the parallel plate capacitor again. This plate's positive, this plate's negative. The electric field in the region between the plates points from the positive to the negative, and in the region between the plates, it's uniform and it's perpendicular to the plates. It points directly from one plate to the other, uniform field, always pointing perpendicular to the surface of the plates. We've seen if I move a charge from the negative plate to the positive plate, I change the potential. But now, let's think about this. I'm going to take this sphere and charge it up positively, and I'm going to move it along the midpoint of the region between the two plates. I'm going to move it from right here to right here. It's always the same distance between the two plates. So I've moved it from a point low between the plates to a point high between the two plates. But what is the difference in potential between this point and this point? We'll give you some choices. Well, the electric field points from the positive to the negative, and so when I'm moving the sphere, I'm always moving it perpendicular to the electric field lines. And because I'm moving it perpendicular to the field lines, I don't have to do any work. There is no electric work done. And so as a consequence, I don't change the potential energy, and so there is no difference in electric potential between this point and this point. No work, no difference in potential. I don't have to apply a force to move the charge along this line. And so as a consequence, this line that's equidistant between the two plates is a line that we call an equipotential line. And we'll show you in the chapter how we can sketch out equipotential lines, equipotential surfaces around arrangements of charged conductors. And you can use the equipotentials to deduce the field, or you can use the field to deduce the potentials, because the equipotentials are always perpendicular to the electric field and vice versa. Now we'll show you how you can do this in practice, how you can make these measurements. This is a piece of conducting paper, and on it we've sketched out two conducting electrodes. And I can establish a potential difference between these two conducting electrodes this way. If I connect this plate to 1.5 volts and I connect this plate to the 0 volt terminal of the battery, there's a potential difference between these two plates, and this is just a parallel plate capacitor. Now what I can do with these two plates is the following. I'm going to stand this up so that we can see it and I can make measurements. I can measure a difference in potential with a voltmeter, and the voltmeter records the potential difference between these two probes. So I'm going to turn on my voltmeter, and if I measure the potential difference between the lower plate and the upper plate, I measure a difference in potential of 1.5 volts. Now we have a question for you. Suppose I measure the potential difference between the lower plate and this point, which is at a midpoint between the two plates. This potential difference is 1.5 volts. What is this potential difference? We'll give you some choices. And in fact, we haven't talked about this, but you can probably guess. This distance gives us a potential difference of 1.5 volts. Right here, I get a potential difference of 0.75 volts. It's half the potential difference of the total potential difference between the two plates. It's half of the potential difference between the two plates because it's half the distance. And the reason the potential scales this way is because the electric field in this region is uniform. So the potential gets steadily higher and higher and higher as I work my way from the lower plate to the upper plate. So the potential exists at all points in space. It's not just at these two plates. It gets higher and higher and higher steadily, and that increase in potential we can think of as actually producing the electric field between these two plates. There's an increasing potential, and so therefore there's an electric field which points downward toward the lower potential. So there's this very, very good connection between the electric field and the electric potential. So if you understand fields, you can understand potentials. It goes so deep that actually the units for electric field that are most useful are units that use volts. I'm going to do a demonstration. I'm going to bring in this Van de Graaff generator here. And the Van de Graaff generator is great because it generates very, very high voltages, lots of charges. This one generates a voltage of probably a couple 100,000 volts. Now, this sphere is going to be at a positive voltage. This one is grounded. 200,000 volts, 0 volts. And so there's a difference in potential between the two. If you let a charge loose from this sphere, it'll go towards this one. And it's a huge difference in potential. And so by the time it goes from here to here, there'll be a huge difference in potential energy. There's a lot of energy which is released in this process. But I want you to think about this. High voltage, 0 volts. What's going to happen to the electric field in the region between these two spheres as I decrease the separation? What will happen to the magnitude of the electric field if I take these two spheres and I bring them closer to each other? We'll give you some choices. Now, as you'll see in chapter 21, one of the units we can use for electric field is volts per meter. It's the difference in potential divided by distance. So if I take this sphere and I move them closer to each other, it's the same difference in potential, but it's happening over a smaller distance. So think about the force that a charge would feel. This difference in potential, if I shrink it into a smaller distance, it's going to be pushed harder in the region because it's got to have a bigger difference in potential energy over a smaller distance. We might say that it's steeper, it's pushed harder, and so therefore this is going to correspond to a larger electric field. Same potential difference, smaller distance, larger electric field. And we have an equation that demonstrates this in chapter 21 that works well for uniform electric fields. And in the region between these two spheres, the electric field is uniform enough that we can use this for a good approximation. So what I'm going to do is turn on the Van de Graaff generator. This one charges up. There's a difference in potential between the two spheres. As I decrease the distance, the electric field increases, and at some point, the electric field is big enough to ionize air, and then, oh yeah, the electric field is big enough to throw a spark. Now think about this. Each time there's a discharge, each time a spark jumps, you see the spark, there's light which is emitted. You also hear the spark, there's sound which is emitted. And so energy is being given off by the system. Energy is therefore stored inside the system. Energy is stored in the separated charges, and we can use this separation of charges to do work, as we'll see in the next segment.